Okay, good morning, everybody. Good morning welcome to the second day of our conference. Today we have Jan Haskovec, which has done physics and mathematics in Prague, and then after went to do a PhD under the supervision of Christian Schmeiser in Vienna. And I think for some time now he's on KAUST and the University of Science and Technology. He has many diverse interests on PD, kinetic limits and macroscopic limits for kinetic models. And then today he's going to talk to us something along this direction, I believe. Discrete and continuum modeling of biological network formation. Jan, thanks so much for coming.
Okay, thank you. Thank you very much for the introduction. And thanks to the organizers for allowing me to being here and speaking here. So two of the organizers are not physically present, but at least present on the slide. So Peter and Benoit. Yeah, it's my first time in IMPA, and first time in Rio, first time in Brazil. So I'm enjoying it very much, and I hope you will enjoy my talk. So if you did some yoga in the morning, I did not, but maybe you did. So for sure you did something good for your cardiovascular system. So this is the first example of a biological transportation network that the talk pretty much will be about. It is known that yoga and meditation is also good for your brain. So this is my second example of a transportation network for information in terms of electrical charge in our brains, in living organisms. And the third example is the leaf venation. So this comes from the plants. And essentially this project inspired me to do something which I never done before. Whenever I was in nature, in forest and so on, I started actually looking in detail on the leaves of the plants, and it's actually quite amazing that actually every plant has a different structure of the leaf venation. So how many different, in terms of mathematics, how many different topologies and geometries you have. So mathematics can be really inspiring you to actually discover things that maybe you would not otherwise look at. Okay, so indeed, biological transportation networks is a fascinating topic, and clearly it's important to understand how they are formed, how they adapt, and how they work with all the possible medical application, for instance, you can think of. So people were interested in modeling these networks. So somehow the interest started in the physics community some years ago, and there the approach was in terms of discrete modeling. So essentially, the transportation network was thought of as a discrete graph, and so the edges of the graphs you can think of as tubes where a material is flowing, blood or water, whatever. And the tubes are connected in nodes. Okay? So then there's been really a family of different models for discrete model for transportation networks, which you can classify into static or dynamic. So the dynamic models take into account also the adaptation of the network to changing external conditions. You can have deterministic models. You can have models with some stochastic element in that, so random graphs. And essentially what we are interested in is what is the optimal structure? What is the optimal transportation structure in terms of the topology of the graph? So you actually see two sort of like extremal examples where on the left-hand side you have a network that is a tree, so you have no loops. On the right-hand side you have a network which has many loops. Okay, so essentially the idea here is that the network should, the graph should model again a plant, a leaf of a plant, and there is the stem here. So there is an inflow of water and nutrients from pretty much this node. And your task is to distribute the water and the nutrients on the surface, on the whole surface of the leaf. So each of the nodes is actually a sink that the water should be going out through evaporation. And you are asked to minimize a certain type of energy functional. And the question is, so what is then the optimal transportation network? So with different settings or different energy functionals, you may get different topologies. Essentially, it's everything boils down then to an optimization problem, and the energy functionals that you have to deal with typically would be non-convex. So then, obviously, you run into troubles with finding global energy minima, and in the discrete setting, this means NP completeness troubles and so on. So let me give you sort of like a short introduction how the discrete model networks. So what is the general framework? So as I said, you start with a graph, which is a set of vertices and edges, and this is an input that you have to give to the model. Okay, so you have to prescribe a certain discrete graph, and on the vertices, you measure pressures of the material flow. Okay, let's say the water in the leaf, and each edge, which is a connection between the two nodes or two vertices, has a certain conductivity. So you can think of the edge as a tube where the material is flowing through, and the conductivity would be typically related to the radius of the tube. If you assume laminar flow, then actually the conductivity scales like a fourth power of the radius of the tube. Okay. So indeed, we assume that the flow is laminar, so Poisson flow. Then the flux through any given edge or a tube is proportional to the conductivity, and it's proportional to the pressure difference between the two nodes that the edge is connecting. And this Lij is the length of the tube, so it's inversely proportional. So the flux is inversely proportional to the length of the tube or the edge, which again, this is something that you have to give as an input. So you give the graph, which is a set of vertices and edges. You give the lengths of the edges, which somehow specifies the geometry of the graph. And then obviously what you have to satisfy is a local conservation of mass. So for every node J, the sum of the fluxes going in or out from the node through the adjacent edges has to be balanced, or has to be balancing the external source or sink of the material. So these Sij are actually, again, something that you have to put as a datum to the model, and they describe. So Sj positive means that there is a net inflow to the node from outside, and Sj negative means there is an outflow. So by the way, Qij means the flow from I to j. So when Pi minus Pj is positive, meaning that the pressure in I is higher than pressure in j, then the net flow will go from I to j. So Qij is positive when you have flow from node I to node j. So that's somehow the framework, and now the question is, what is the energy functional that you want to minimize at the end of the day? So now you can have many different choices, many different models. Let me focus on a model of Dan Hu and David Tsai, and they consider the energy functional of this form. So let me actually explain it. It contains it is composed of two terms. The first term is the pumping power. So if you think in terms of cardiovascular system, your heart is pumping the blood through your body, and this, of course, costs some energy. And by the Joule's law, the energy is actually equal to the potential difference, which is just the difference of the pressures, times the current, which in our notation is this Qij. This is the flux through the edge. Okay, so I can use this formula to express the product of the potential difference and the current in this form. Okay, so and then I sum over all edges that I have in the graph, and this is the first term. Okay, so you see I'm summing through all edges. Qij squared over Cij times Lij is this term. Okay, so the first expression here just amounts to the physical energy consumption of pumping the material through the network. The second term is related to somehow the biological nature of the transportation network, and it's the metabolic cost. So essentially, biological systems are trying not to be wasteful. So whenever you have a certain structure that you have to maintain, again, it costs you some energy, right? Or the structure is composed by living cells, and the cells have to breathe and so on. So again, whenever you have some structure, it costs you some energy to maintain it. So for certain biophysical reasons, it's a good idea to assume the metabolic cost to be proportional to some power of the conductivity. So meaning that if you have a larger tube, then it has a more energy consumption. So I do not want to go too much into details, but there is something that is called a Murray's theory for blood flow, and this tells you that actually the power gamma here is equal to 1/2 for blood flow, and for leaf venation, somehow the reasonable choice of gamma is between 1/2 and 1. Okay, so the energy is just the sum of these two contributions, the pumping power and the metabolic cost. Clearly, the energy as a function of C of the conductivities is a non-convex quantity. So how do you like to minimize it? Well, there are many methods that you may choose from. So let's say one of the most straightforward is just to consider the gradient flow of the energy constrained by the Kirchhoff law, which is just the local conservation of mass. And when you do that, it's maybe not the smartest way how to find the energy minimizers, but anyway, it gives you a nice interpretation in terms of adaptation, and so it gives you a system of ordinary differential equations for the conductivities of each edge, and you can actually interpret it as let's say, as an adaptive system. So you can start playing with the data and see how the network adapts in time to changing conditions. Okay, so yes.
I'm trying to appreciate the differential equation.
This one, yeah.
It's independent for every INJ, or there are summations?
So you have to. So this ordinary differential. So there's a system of ordinary differential equations. It's coupled to the Kirchhoff law, which is of this form. So essentially, as written here, it looks like being local in IJ, but the coupling of the different edges comes from this term Q, which is for a given set of conductivities, is the solution of the Kirchhoff law. So indeed, everything is coupled together.
Pressures are also knowns, or they are
No. The pressures, you actually you calculate them by solving the Kirchhoff law. What I should have said, yeah, if so essentially for a given set of conductivities, this is a linear system of equations, which may or may not be uniquely solvable. And as a matter of fact, if and only if the graph is connected, then you have, so essentially it's a graph Laplacian. So you have the Fiedler number and so on. So if and only if the graph is connected, you have a unique solution in terms of pressure up to an additive constant, which is very natural because, yeah. Yeah? Deeper? You minimize in terms of conductivity, so you are trying to find the optimal conductivities of the edges for given data in terms of the sources and sinks. Okay, so maybe going back to these pictures, essentially the thickness of these lines actually is proportional to the conductivity. So you see, as I said, there is an inflow here, so you have to transport all the material through these edges here, and then when you are going further, the edges are getting thinner because you don't need so much capacity anymore, right? So essentially here, what you have as a data is the graph and is the sources and the sink. So in this case, there is only one source, one big source, and the sinks are distributed everywhere around the surface of the leaf. And what you are trying to find is the optimal conductivities of the edges. And the pressures actually, or the fluxes, you calculate by solving the Kirchhoff law. Okay, fair enough. So the starting point of our work on this topic was the idea that you have a discrete system. So is there something that could be that you could understand as a continuum limit of the discrete system? So when the number of edges and nodes goes to infinity in some way, so can you do something like a mean field limit of this system of ODEs coupled by the Kirchhoff law? And what would you get? So you expect to get some system of PDEs, right? So how the system of PDEs should look like. Now, the problem is that this is a much more complicated problem than mean field limits of interacting particles, because there is just much more structure. It's not even clear when you have when you want to construct a sequence of graphs that are finer and finer, so having more and more edges and nodes. Right? What is the topology of the graph? What is the connectivity of the sequence of the graphs and tends to infinity and so on? So I hope I will have time to actually speak about or say a few remarks about the problem of continuum limits of graphs. So what we did is very, let's say, very non-rigorous approach, which I ask you to accept. Let's say that the idea is that if you get something in the mean field limit, we assume that it should look like a porous medium, like a porous media flow. Okay, and the porous medium is described by a permeability tensor, and essentially what we would like to do is to locally identify the direction of the edges and their conductivities with a certain vector field that we described, that we denote by M. And as a matter of fact, we would like to have the permeability of the porous medium so the highest permeability in the direction of the vector M. And in the directions orthogonal to M, we do not want to have any permeability of the medium. So this is like the principal direction should be always the principal direction of the flow should be always aligned with locally with M of X. There is in the theory of porous media flows that are thought of a system of interconnected tubes. There is the so-called Karman-Kojen equation that tells you that the permeability is scales like the squared of the radius of the tube. So what we do is to identify the radius of the tube locally with the magnitude of the vector m. And again, we would like to have a permeability, the principal permeability aligned with m. So then essentially the only choice is to write the permeability tensor as the tensor product of m with itself. Because then the principal eigenvalue indeed is m squared, and this is r squared. So the principal eigenvalue is the permeability of the medium. So this is indeed kappa r squared m squared. And the corresponding eigenvector is the normalized vector m. All the other eigenvectors are orthogonal to m, and there is zero permeability in those directions. Okay, so the idea is to identify the conductivities of the edges in the discrete model with the magnitude squared of the vector field m, and the directions of the edges with the direction of m. Then you want to turn the discrete pressures in the nodes into function, right? So you just, instead of capital Pij, you write a small p of x. And then the fluxes, you want to have a continuous vector field Q that describes the local flux. And so once you have the permeability tensor and you have the pressure function, then for the porous media you have the Darcy's law that tells you that the flux is minus permeability tensor times the gradient of the pressure. And formally, the discrete Kirchhoff law, which essentially means the local mass conservation, turns into a Poisson equation where you have the divergence of the flux equal to the sources or sinks. So the flux is this expression. And S is again, this is a datum that you have to prescribe for the system. Now you may already start complaining because this Poisson equation with this permeability tensor in general is not well posed. This is not an elliptic equation, but for the time being, let's accept it as an equation that we would morally like to solve, and later we will deal with this problem. Okay. So in the end of the day, what you get is again that's the Poisson equation, which is essentially should be the mean field limit of the Kirchhoff law, and then for the vector field M, which is again locally the principal direction of the network, you get a system. Because M is a d-dimensional vector, right? So you get a system of equations. Essentially, it's this term corresponds to the orientation of the network. So it tells you that it makes sense to orient the network or the tubes along the pressure gradients, and this term corresponds essentially to the metabolic cost. So it tells you that if you do not need the structure, you just let it decay. It's essentially a decay term, right? And again, this system is a formal L2 gradient flow of this energy functional. So you can understand this energy functional again as a continuum limit of this energy functional. Okay, so again you have the pumping and metabolic terms. So that's the pumping term, that's the metabolic cost. And if you write down the formal L2 gradient flow constrained by the Poisson equation, you get exactly this system. However, there are some problems. Essentially, there are two problems that we have. So the first problem I already told you, this equation in general is not solvable because of the degeneracy of this tensor. So we have to fix it somehow. So we have to, let's say, put more, let's call it modeling assumptions. And somehow the easiest fix is if this field is degenerate, well, let's just introduce something that can be understood as isotropic background permeability of the medium, meaning that you just add a multiple of the identity matrix, which makes the permeability tensor, at least for bounded M, an elliptic. So it turns the Poisson equation into an elliptic problem. So again, this is not too stupid to do because again, it's from the modeling point of view. What we are doing is adding a background permeability that is isotropic in the medium. Okay. Now the second problem that we have with this system is not that obvious, but if you take a look at this equation, the M equation, it is essentially local in X. So there is no X derivative here. So if you start with a compactly supported initial datum, and so you will stay there. So if you have a domain and prescribe an initial datum in part of the, so supported in part of the domain and 0 otherwise, so M0 otherwise, it will stay 0 for all times, right? Because there is nothing that would push it away from 0. So again, this is something that we don't like that much, especially the idea was that we would like to have a, yeah?
Did I get this right when you said it? So the discrete approach was only about finding the conductivity, so the flows for the network topology.
Yes.
This continuum approach is also about finding...
It's about finding the M's. So the energy is to be understood as energy functional in terms of the M, which is the conductivity field, so the vector field that describes the conductivity. So what we did is the discrete problem is to find theseCij's. The continuum problem is to find this vector field M. Okay.
Does M also includes information on the network topology?
So the question is in the continuum setting, what is the network topology? Yeah? So the network topology in the continuum setting is encoded by the vector field M. Yeah, essentially, yeah. Because once you have the network topology, so once you know the vector M, then you calculate the pressure by solving this, or actually by solving this equation. Okay, so S is a datum, S are the sources and sinks. So once you know M, you calculate your P, and then actually the flux through the network is this given by this expression. So once you know M, which is like the network structure, you calculate the flux, so you know how the thing is flowing then inside.
This is more than just the continuum limit of the discrete model. You put something in, I guess.
As I said, it's a very non-rigorous way of deriving the continuum limit. We are working on more rigorous way, but this is somehow still a work in progress. And yeah, you can see it as a enhanced model where we put some more modeling assumptions into that. But again, this is due to the fact, as I said, it's a way more complicated problem than just taking a set of interacting particles and deriving the limit as n goes to infinity. It's not so. Essentially, in the interacting particles case, you more or less only it's the question of the scaling. How do you scale the interactions, and then this gives you your PD system. Here it's the question, what is even, so how do you construct the sequence of discrete networks that are growing in size? And that's a very, very non-trivial thing, as I hope we'll have time to discuss. So, okay, so going back to this slide, so we have these two problems that we fixed. Did I tell you how do we fix? No, I didn't tell you how we fixed the second problem, so the locality in X. Well, again, we introduce diffusive term in M, which again means that you have some noise in the system, some noise in the network, and this is modeled in the simplest way, just as a diffusion in the vector field. Okay. So the question is, by doing these two, let's say, modeling assumptions, did we destroy the energy flow structure of the system? Fortunately not, so you just have to modify the energy function, you add these two terms, and then still this system is a gradient flow of this energy. So to, yeah?
First problem.
Yeah?
See that there is a problem of degeneracy in the paired direction of m with respect to the gradient of p, because then you have zero when the gradient of p to the tensor, right?
Yeah, yeah.
But the flow is generally the direction of the gradient of p. So this in fact doesn't matter, because there's no flow, there's no perpendicular to the gradient of pressure. That's the Dayse's law.
Well, so first of all, it can happen too that, again, let's say you start with a compactly supported initial datum, so m is 0 somewhere, and it's so to be able to solve this equation, s would have to 0 also, so s would have to have or is not allowed to have a larger support than m. That's the first thing. And the second thing is it's not also not well posed as a boundary value problem, because if you consider m to be just a vector field in this direction, so you have a square and m is in this direction, so you have to prescribe boundary conditions on the two vertical edges, but not on the horizontal ones. And if you turn m in that direction, then you have to change the boundary condition. So actually, it's also the boundary condition would have to be compatible with the vector field. Yeah. So I mean, again, this is quite an interesting problem. So I'm not saying that this problem is unsolvable, but it's just you would have to actually work and develop a solvability theory for this problem. And again, this is not that clear, not that straightforward. Yeah. So probably given the compatibility conditions on the boundary datum and on S, then you can construct a solution, I guess. Okay, so this is just an overview slide. So what we did a lot of things. So in the end, what is the system that we are interested in? So we have a Poisson equation for pressure, given the vector field m. And so this is the isotropic part of the permeability. So R is a given function against the datum of the system. S is the source, is a sink, again, datum. And this is coupled to the reaction-diffusion system for the conductance vector m. So this is a d-dimensional system where d is the dimension of the space. And you have essentially three terms. So the first is corresponds or describes the random effects in the porous medium. The second term we call the activation term. So this c squared is just the constant, again a datum, or parameter of the system. And again, this tells you that it makes sense to orient your network along the pressure gradients. And finally, this relaxation term tells you that it costs you something, that there is a metabolic cost related to the structure that you have. So again, C is an activation parameter, D squared, or D is the diffusivity, and gamma is the relaxation exponent. You have to prescribe some reasonable boundary conditions and initial condition for M, and then you may to try to solve the system. So yeah, let me show you first numerical result done by Matthias Schlottbaum. So what you see here is, again, we are trying to model a leaf of a plant. So our domain is essentially this squared. We prescribe an influx from here and outflux everywhere on the surface. And what you see here is the logarithmic plot of the magnitude of M, and this is the corresponding pressure field. Okay, so what your question about the topology of the network is, if you plot it nicely, then the vector field M, indeed, if you solve the system, looks like a network. Okay. So I just should comment this white here doesn't mean that M is equal to 0. It's just that there is a cutoff. So if M is smaller, the magnitude of M is smaller than something, then you don't plot it anymore. But you see also here that you have quite large gradients in the perpendicular direction to the network.
Isn't there like this branch in the middle that ends up not at the boundary and also not go up, moving up?
Pardon me?
I wonder whether there are dead ends in the network. But
Dead ends?
yeah, like there's one branch not exactly in the middle, but
Uh,
top of the center. Yeah, just next to the network. Yeah,
Le-
that one also. Yeah, this one.
This one. Yeah, it's you know, it's a continuous structure. So yeah. So the question is if there are dead ends in the network. The question how you define a dead end in a vector field is still the way it's plotted. It pretty much looks like sort of a discrete structure where you can say there is a dead end or not. But in fact, this is just a function, a continuous function on the domain. So it's not even so clear what you mean by a dead end. But yeah, we didn't really look into that. Like, yeah.
So it makes something like this, and then it goes below the threshold for a bottom.
Yes. Yeah. Okay, so the message is that it seems to be interesting to indeed study the system and try to develop a theory, a mathematical theory. So again, we know that the system is a constrained formal L2 gradient flow of a certain energy functional. So if the energy functional was convex or lambda convex, there would be essentially the existence story would be almost for free, but this is not the case. So the energy function is not convex. I mean, these two terms, the first two would be convex at least for gamma larger than 1/2, but these two actually destroy the convexity properties. So you cannot use the established theory of lambda convex gradient flows. So essentially, the only thing that you have is the a priori estimates given by the energy dissipation. So you have to work to show existence of solutions, and so when you start looking at the system, so you want to iterate, right, between M and P. So you start from, let's say, looking at the Poisson equation. So you say, okay, so if M is reasonable, then you use Lax-Milgram for constructing solution P, the pressure field. So P is an H1 function given by Lax-Milgram. So gradient P is in L2, gradient P times gradient P is an L1 function then. So what you need to give meaning to this term is that M is L infinity, right? So essentially what you are asking from this equation is a maximum principle. But this equation doesn't satisfy any maximum principle precisely because of this activation term. You may try to do some Nash-Mose iterations, but again, this doesn't work precisely because of this quadratic nonlinearity is too strong somehow. So you are getting into troubles. Then you say, okay, so why don't I use something better than Lax-Milgram, right? It's an elliptic equation, so I have elliptic regularity results. So gradient P should be much better at the end of the day than just L2. But the problem is that ellipticity means not only that the eigenvalues of the tensor are bounded from below, but also from above. So for boundedness from above, you need M bounded, right? M in L infinity, which is precisely that you don't have, okay? So it's not so clear but how you will proceed, and you have to have some good ideas. So essentially, yeah. Another problem is that if you do the iteration between N and P, then in general you may destroy the energy dissipation and you will lose your a priori estimates, right? So what are the good ideas that you need to do? So you want to get rid of the problems with gradient P times gradient P being only an L1 function. So you actually want to either cut off or regularize, mollify something, and you want to mollify in such a way that you actually do not lose the energy dissipation structure. So what you see here, actually, these two terms somehow are talking to each other. So you have an MM gradient P and you have M gradient P. So you want to actually modify both terms in a compatible way such that you still have an energy functional. And so if you do it in this way as written here, then essentially you still have energy functional. And another sort of trick is what kind of modifier you would use. So using the standard modifier, this compactly supported thing, is not such a good idea, because what you want to do at the end of the day, so when you, let's say, multiply this equation by P and integrate by parts, you get an integral from this term. You get an integral like that, and you would like to know that this integral is bounded from below. It doesn't have to be positive, but you need, for the a priori estimates, at least boundedness from below. So you have integral of the type some function times the function convoluted with your modifier. Is this bounded from below or not? Because this function doesn't have a sign, right? It can be positive or negative. So as a matter of fact, if you use, instead of the compactly supported modifier, you use the heat kernel, then by a very simple exercise in Parseval equality, if you turn to the Fourier domain, you can actually, it's a one-line proof. You can prove that this expression indeed is bounded below. Actually, it's non-negative. Okay, so that's another trick. Essentially, for the modification, use the heat kernel. So the problem with the compactly supported modifier is that nobody knows what is the Fourier transform of it. Okay, for the heat kernel, you know it, right? So essentially, you have you regularize the system such that you get rid of the problems with the with the ellipticity and unboundedness here. You conserve the energy dissipation structure, so you have a priori estimates uniform in epsilon. So then you can, using another slight tricks, you can make the limit epsilon going to 0 and indeed recover the solutions, so weak solutions of the system in the energy space for gamma. So this is the metabolic exponent larger than 1/2. So the system, if you look here, this term still should make a good sense for gamma equal to 1/2, and in fact this is the relevant exponent for the blood flow. So it is indeed interesting to study the borderline case where this term is not yet degenerate for m equal to 0, but for gamma equal to 1/2, this is m over magnitude of m. So you have the mild singularity at m equal to 0. So for gamma equal to 1/2, yeah, so as I said, this is m over, the metabolic term is m over magnitude of m. And still you are in a good shape because this corresponds to the L1 norm. So the differential of the L1 norm is formally this one, right? So you have to turn the parabolic equation for m into an inclusion where the metabolic term you write as a subdifferential of the L1 norm, and then you can use the theory that is there for differential inclusions to indeed actually do the same program as before, with even slightly more tricks to show solutions even for gamma equal to 1/2. The problem is that what we don't know, that m, we suppose, or we believe that m at the end of the day is the so-called slow solution, meaning that for m equal to 0, this expression is indeed the minimal, the element with the minimal norm, meaning 0. But this is just a conjecture. We do not know if this is indeed true. Okay. Mild solutions. So let me just, this story was about constructing weak solutions. We are also able to construct mild solutions in somehow a little bit exotic function spaces of functions with vanishing mean oscillations using somehow weird perturbation theories. But maybe because of time, let me skip this one. And let me also, this is related to that. So the more interesting message maybe is, so in the end, how the system, or how we think that the system is generating these interesting network patterns. So essentially, it's an interplay really of all these three terms. So you have the activation term that that propagates the network along the pressure gradients. You have the relaxation term that essentially is a decay term, so it's propagating the sparsity in a way. And then the diffusive term essentially is responsible for growth of the network. So if you start with a compactly supported initial datum, then the diffusive term will propagate the values into the domain, and then the activation term and the decay term will start, building the network structures somehow. So this is crossed out. So just as a remark, if D was 0, so if this term was not here, then the support of the initial datum just would not grow. Okay. So the network structures at the end of the day are the stationary solutions of the system. So clearly you have trivial stationary states where the M is 0, there is just no structure anywhere, and the pressure just satisfies the Laplace equation. The question is, do we have and can we construct non-trivial stationary states? Indeed, yes, we can for certain parameter values. And again, the way to do that is to use some nonlinear perturbation theory by Rabinowitz and friends. So the message here is that we also have existence of non-trivial stationary states, which we believe are the network structures that you see as an example in the numerical result. You can also play a game and try to construct the steady states sort of explicitly, which is possible if you forget about the diffusion, which I said is not a good idea. But if you actually do that, then you see that the stationary state satisfies this equation. So essentially, it's an eigenvalue problem. So eigenvector, eigenvalue problem for the permeability tensor of this form, which you then insert into the Poisson equation. And what you get is some interesting nonlinear elliptic equations, which, however, in certain cases you can solve. So in particular here for gamma larger than 1, you can construct a solution just by calculus of variations, because the corresponding function is a convex one, strictly convex. For gamma equal to 1, the situation gets even more interesting, because then you get a very highly nonlinear elliptic equation, where here you have actually characteristic function of the gradient of the pressure of the solution being equal to a constant. So, but again, this problem actually is solvable. Okay. Numerical results. So what we try to understand is actually how the network structure depends on the parameters, the values of the parameters. So what we always did is to start with a certain setting and keep everything constant and change just one parameter and see what is the effect. So here we have certain settings for S and the activation parameter and gamma equal to 1/2, and we change the values of the diffusivity. So with in fact, the diffusivity must not be too high, because otherwise the diffusion will just destroy the network structure. So you will, for high D, you will get a pattern, but not really a network pattern. Okay. So for D equal to 10⁻², you get a steady state that looks like this. And when you decrease D further, you see that you actually are getting more branches, and the branches are getting thinner. So this is to be understood that essentially the diffusion has a smearing effect. Okay, so with higher diffusion, you get sort of like a rougher network, and when you decrease the diffusivity, the network is getting more let's say, finer with thinner structure and more branching. When we change the value of the metabolic exponent gamma, so I said gamma equal to 1/2. This is the borderline case. This is the least meaningful value. So in that case, you have a structure like this. And when you increase gamma, you see that you have like the network is getting denser. And then finally, for gamma equal to 1, the steady state is still a non-trivial steady state, but there is no identifiable network structure anymore. So indeed, the system produces interesting solutions in terms of network formation in the range of gamma between 1/2 and strictly less than 1. Okay. Finally, this is a nice example where we actually put one source and two sinks. So this is like approximation of Dirac delta, and this is approximation of -1/2 Dirac delta, and the same here. And let's just do the system the work, like do this, let it connect the source to the two sinks, and watch how the solution changes with changing values of gamma. So this is for gamma equal 1/2, and here you see actually the effect of the metabolic term. So for small gamma, it is better from the energetical point of view to first flow together, so to one pipe for the whole flow, and at some point clearly you have to bifurcate. But so the smaller the gamma is, the longer you want to stay together. So this is actually related to the convexity concavity properties of the metabolic term. So for gamma equal to 1/2, this is the strongest concavity, meaning that you want to transport the things together and bifurcate as late as possible somehow. And when you increase gamma, so you are actually decreasing the concavity of the metabolic term, you see that the bifurcation happens sooner. So here is gamma equal to 0.6, 0.8, 0.9, and then finally for gamma equal to 1, you actually bifurcate immediately and then just have two linear tubes connecting the source to the sinks. Okay, so this is actually the effect of the concavity of the metabolic term, and somehow is related to the branch optimal transport in certain ways. I'm almost running out of time, maybe let's leave the slide for later. What I'd like to just make a remark is the problem of the continuum limit of graphs. So indeed, this is a very, very interesting problem. So this is something that has been studied in the graph community for some time, and the motivation for this is the following. So essentially, if you have a first semester students, so you probably tell them the story that why do we need irrational numbers? Well, because you have certain equations or certain minimization problems that are reasonable, but the solution is not rational. So in the same way, you have certain questions about graphs, finite discrete graphs, that are reasonable, but there is no finite graph that is essentially answering the question. There is no minimizer as a finite graph. So here actually the question is if you want to find the minimum, so within the class of finite graphs, the minimum of the proportion of squares in the graph with all graphs that have the proportional of, so the density of edges is larger than 1/2. I mean, this is a certain graph theoretical question that is reasonable, but there is no minimizer. So that's the motivation to consider something that is a limit of a sequence of finite graphs. That would be, in the end, your minimizer. And there has been a lot of results about that. Essentially, the Hungarian school, the Hungarians are actually very strong in graph theory. So the theory is well defined and developed for a dense graph. Dense graph means that the number of edges scales quadratically with the number of nodes. So then essentially you define a limit of a sequence of finite graphs in terms of a subgraph density. So you calculate the number, so you fix a graph F, small graph F, and you calculate the number of copies of the graph F in your graph G, or essentially the probability of finding the graph F when you just choose randomly a K subset or K nodes of the graph G. And you actually define the limit of the sequence of the graphs as essentially, so you say that the sequence is converging if and only if the sequence of the densities for each graph F converges. So the graph F you can understand as a sort of like a test function in the in terms of weak solutions of equations. Okay. So for dense graphs, so for sequences of dense graphs, there is a well-defined limit object. So as I said, dense graph means that the number of edges scales quadratically with the number of nodes. But the problem is for our use is that what you saw in the pictures in the very beginning, important class of the optimal transportation networks are trees, and trees are not dense. Yeah, trees are actually the opposite of dense. They are very sparse graphs. So as a matter of fact, there is not really a developed theory for, or actually it is known that for sparse graphs, the notion of a limit of a sequence of graphs is not a well-defined object. Okay, so how does it work for the dense graphs? Essentially, if you take the example of a bipartite graph, so a sequence of bipartite graphs, so you just write down the adjacency matrices. That if you, I mean, the question is how do you order the nodes? But as a matter of fact, there is something that is called a regularity lemma that tells you that there is one reasonable or one particular ordering of the nodes. And if you do that, so then essentially it makes sense to consider the limit of the adjacency matrices. Okay, and for the bipartite graph, essentially the limit of the sequence of bipartite graphs as n goes to infinity is represented by this adjacency matrix. So essentially the limits of dense graphs are measurable functions on the square. Okay. So the reason why the theory works well for dense graphs is that the regularity lemma in fact tells you that dense graphs somehow behave morally as random graphs. Okay, and then you can construct limits, and they are called graphons. And as I said, the graphon in fact is a measurable function on the square, which tells you who is connected with whom. Okay. So somehow here the theory is existing, and you can see it as an equivalent of limits of interacting particles. Now the problem is, again, for us, the graphs, we have to take into account the sparse graphs, and then the theory is essentially getting difficult, and the problem is that then you actually cannot define anything that you would call a graph limit, okay, or limit of a sequence of graphs. So yeah, my time is over. So the message here is that for us, we have to somehow try to find some workaround about the problem with the graphs, the limits of sparse graphs. So idea would be to use a gamma convergence for the sequence of energy functionals, and see what happens there. And this is just the thing that is the work in progress. Okay, so hopefully next year I will be able to tell you more how to derive the PD system in a more rigorous way from the discrete system than we did so far. Okay, thank you.